Calculus Curve Sketching Part 3. In Part 2, the last video, we dealt with horizontal and vertical asymptotes. Now we're going to deal with oblique asymptotes. They are angled lines. Neither horizontal nor vertical, not a multiple of 90 degrees. We do also have curved asymptotes, but we're not going to deal with them in this course. Here's some examples of oblique asymptotes. And those are all possible curves. Those are actually all very straightforward curves, generally hyperbolas with something added to make them asymptotic. And while we're dealing not with curves, let's have a look at a couple. They're quite interesting. Here's y equals 1 over x, asymptotic with y equals sine of x. Interesting. It behaves like y equals 1 over x when sine of x is pretty much 0, when x is pretty much 0, but after that it's going to hug closer and close to y equals sine of x. Here's y equals 1 over x, asymptotic with y equals x squared. Very interesting. So, oblique asymptotes occur when functions approach other functions as x tends to infinity. Have a look at this one. Here's the function 1 over x. Now, as x tends to infinity, 1 over x tends to 0. That tends to 0. So as x tends to infinity, x plus 1 over x will tend to x plus 0, which is x. So what we're saying is that is tending to x as x tends to infinity, which means y equals x will be an asymptote. Let's have a look. There it is there. We saw it earlier. Now you notice that there's a vertical asymptote, the y-axis. Well, here we are. Find a common denominator, and the limit of that as x tends to 0 is infinity. So there, x equals 0 is your vertical asymptote. And of course, as we reasoned earlier, y equals x is your other asymptote. Let's derive a couple of formulae. We have two formulae to give you the values of m and c for these linear asymptotes, or you can do it by another method which involves long division. You can make a choice as to which you use. One thing you must know, though, is that these formulae do not usually appear on formula sheets or information booklets, so you need to remember them. But there are easy ways to remember them. So what I'm going to do is I want to know m. And to do that, the first thing I'm going to do is I'm going to take that whole mx plus c to that side. It seems strange, why not just take the c across, divide by x, but that's not going to give me what I want. So just bear with me that I'm going to take that across n block. And I'm going to shove it inside the limit. Because in fact, the limit of mx plus c, as x tends to infinity, is mx plus c. The only time a polynomial, well, not even a polynomial, one of these functions does not approach itself as x tends to infinity is if you have x in the denominator. Then it causes funny things. So therefore, I've taken mx plus c, taken it across n block in a bracket to the other side, minus mx plus c, and I'll put it inside the limit side. Now I'm going to fiddle with that. I want to get rid of the x, so I have m on its own. So logically, I'm going to divide each side by x. So we have that. Divide by x, minus c divided by x, 0 divided by x. There we are. Now if you look at c over x, we can already tell what that's going to go towards as x tends to infinity. 0. Therefore, we're now down to just that and that inside the limit. But now what I've done is I've taken the m out of the limit, which I'm allowed to do because it's a constant, so I can go on the other side. And there is our formula for the gradient of an oblique asymptote, a straight line linear asymptote. And we'll look now at how that comes about. Tough to remember? Well, not really. What's another way we refer to f of x, often, especially in graphs? Y. So f of x over x means y over x. Where have we seen y over x before? Oh, gradient. Change in y over change in x. So all this says is the limit as x tends to infinity of the gradient is equal to m. Try to remember it that way. We say, well, put y over x, f of x over x, find its limit as x tends to infinity, and that'll give me the m value of the y equals mx plus c asymptote. Now I'm going to do a far simpler fiddle for the c value. The c value, I can just take the mx to the other side. So there we are. I can include it inside the limit sign because the limit of mx is the same as mx. Here it is there. How do we remember this? Well, we're looking for the limit of x of f of x as x tends to infinity is mx plus c because it's the oblique asymptote. Take mx away from mx plus c, we end up with c. Oh, mx plus c minus mx gives you c. Let's do a couple of examples. There the formulae are for now, but you need to memorize them. Now, I know this has an oblique asymptote because polynomial over polynomial, we're not going to go into other mathematical functions and confuse the issue. Degree of numerator exceeds the degree of the denominator. So therefore, there are asymptotes. There's an asymptote, R or is asymptote, which is not vertical or horizontal. For it to be linear, the degree of the numerator must be only one more than the degree of the denominator. So if this was x cubed, that would have to, the degree of the top would be 4. If that was 4 and this was 2, then the difference would be squared, the degree of 2, and your oblique asymptote would actually be a parabola with x squared. But we're not dealing with those. Let's now use the formulae. There we are, f of x over x. Now, when you divide by x, it's the same as multiplying by 1 over x. So therefore, we're going to say x times the bottom line. There we are. How do we find a limit as x tends to infinity? Divide through by x cubed, top and bottom, the highest power. X cubed over x cubed, x cubed over x cubed, x over x cubed. Now, as x tends to infinity, 1 over x squared is going to 0. That stays as 1, that stays as 1, so we'll have 1 over 1 plus 0, which is 1. Therefore, we now know that our oblique asymptote is y equals 1x plus c. But we still don't know the c value. Let's use our c formula. So, the function minus 1x. 1x, there we are. Find a common denominator, simplify. Now we want the limit as x tends to infinity, and by now you should be okay on those. It's 0. Our oblique asymptote, 1x plus 0. Let's look at another one. In fact, you try this one yourself first. Get the oblique asymptote. And so we apply the formula, y over x, so that over x, and remember, dividing by x means we multiply the bottom by x, so we have that. Finding the limit as x tends to infinity, divide through by x squared. That That should be x squared, sorry. The top line, that's naught, so therefore the limit is 2 over 1, so therefore m is 2. So now we have y equals 2x plus c. Now we're going to use this formula to find the value of c. There's f of x minus mx 2x. Simplify, there we are. Divide through by x, 5 minus 4 over x, 1 plus 1 over x. 4 over x, 1 over x go to naught as x goes to infinity. 5 over 1, 5. There is our mx plus c. 2x plus 5. Now another way to do it, which you may prefer, but you've got to go back to more basics, that is straight long division. Have a look. I've divided x squared plus 1 into x cubed. The answer, x, remainder, negative x. Which means if I write it back here, I'll write x minus x over x squared plus 1. What I'm saying is that divided by that gives me x. There it is. Remainder minus x, that still has not been divided. I'm not able to do that division, so I write it like that and leave it for somebody else to do. And as x tends to infinity, that's going to go towards 0 because the degree below is higher than the degree above. Divide by x squared, top and bottom, you'll see that. There we are. If I do that, we're going to end up with y equals x. Have a look. Magic's magic. There we are. There's the number there. That's left. That's going to go towards naught. Degree lower than that. So, if you do it by long division, whatever your quotient is, without the remainder, there is your oblique asymptote. There we are. Let's have a look at this one. Do your division, 2x plus 5, remainder minus 9, which means we're going to get 2x plus 5 minus 9 over x plus 1. Leave that for somebody else to do. As x tends to infinity, this is going to naught, and we're going to end up with that. There's your oblique asymptote. Y equals 2x plus 5. It's the quotient part of the division. Let's draw a graph. So we're going to go through the steps. I'm not going to labor the point with the graphs because we've done a lot of them already. So we're just going to practice, and I'm going to concentrate more on the oblique asymptotes. Y-intercept 2. X-intercept, just remember, if you've got a fraction and you want it to be 0, the important thing is the top line. And for that to be 0, x is negative 1 or 2. Vertical asymptote. Now for vertical asymptote, I'm going to find the value of x that makes this tend to infinity. X equals 1. Horizontal asymptote, I'm going to find the limit of that as x tends to infinity. And then none. The limit does not exist of f of x as x tends to infinity. Oblique asymptotes. Now I'm going to apply my formula. Remember, m is the gradient, the limit as x tends to infinity of the gradient. Therefore, the limit as x tends to infinity of f of x over x. And it works out as 1. So far we have y equals 1x. C is the limit of f of x as x tends to infinity, and take away the mx, so we're left with c. Do that, and we get an answer of 0. 1x plus 0. So there is our oblique asymptote. There's by division. X as well, so oblique asymptote is 1. Is y equals x. Now we're going to draw the graph. So, stationary points. Oh, let's do that first. There we are. First derivative, differentiate. Simplifies to that. For that to be equal to 0, the top line must be 0, and this quadratic equation has unreal imaginary roots. You cannot use quadratic formula. You end up with a negative inside the square root sign. No zeros. Therefore, no stationary points. Vertical asymptote, x equals 1. Oblique asymptote, y equals x. The intercepts. Now, let's do some reasoning. This graph is going to approach closer and closer to that line and closer and closer to this line. Is it going to do it on the inside or the outside? Well, the one way to do it is to test a point here, test a point here. Well, the other way, and see where the graph lies. The other thing is to know, well, it cuts the x-axis here, so it's got to be on the outside, the x and y there. And the other way to look at it is, I'm just showing you different ways of seeing how to position it. The best guide is the intercepts. But the other way to look at it is, it has no stationary points. If it was on the inside, it would have to have a stationary point. So therefore we know it's tending to the outside of those lines. And therefore, there is our graph. Let's try this one yourself. So pause and try it yourself. Okay, let's go through this one briefly. Y-intercept 2.5. X-intercept negative 2,8, 1,8. Equal to 0, I had to use quadratic formula. Vertical asymptote, x equals 2. There we are. As x tends to 2, that tends to infinity. Oblique asymptote. I haven't even looked at horizontal asymptote. Degree exceeds degree, so the limit as x tends to infinity of this does not exist. Oblique asymptote. There's our formula for m, and we get 1. Formula for c, substitute in, simplifies to that, and we get 3. Alternative method, long division, and we end up with x plus 3. There we have 1x plus 3. So therefore we know that our oblique asymptote is y equals x plus 3. Stationary points. Derivative using quotient rule simplifies. Our top line will factorize. When you put dy by dx equal to 0, you get 1 or 3. Sub to get your y value. Substitute into the original. Now we need to know the nature of those. So we take the second derivative. Notice I haven't even simplified it. I just say, well, if I put 1 into there, what am I going to get? And if I put 3 into there, what am I going to get? I get a positive. Local maximum at 1, local minimum at 3. Let's draw our graph. They're the intercepts on the axes. Vertical asymptote, x equals 2. Oblique asymptote, y equals x plus 3. There we are. Stationary points, there we are. And in fact, it's pretty clear where these graphs are going to be. But just to reinforce that, there's the turning points, the shapes of them. That's where it's going to approach. So there is our curve.